Usually a duck can quack, can swim, and you can, if you have it on the screen, you have to display it, okay? So this is an abstract class, which you can see these are italics. And these operations are implemented. So there is an implementation of quack, implementation of swim, and implementation of display. Then you have two different ducks, a mallard duck and a red-head duck. Typical ducks swimming around in our European lakes. And you have to override the display method because a mallard duck looks different than a red-head. So this is a simple kind of implementation of this duck problem. At the end, you can show on your screen a mallard duck and a red-head duck. Okay, we will exchange that, okay? Okay, first we will let them fly. What we implement a fly method. So now they can fly. Are you happy with the solution? Okay, I haven't expected any other. Now we add another duck. A rubber duck. Do you know a rubber duck? Little boys have rubber ducks when they go into the bathtub. It's not a real duck, it's just from plastic. Okay? So this rubber duck is something to play for little children to play with it. Okay? But it's a duck. Okay. Can this duck walk? No, not really. It makes squeak, squeak, but it doesn't quack. They have to override the quack method to squeak. You extend this. And you have to change the display method that it looks like a rubber. Okay, that you have to do all the time. Okay, now I ask you, can the rubber duck swim? Yes, it can. Can the rubber duck fly? Not really. Okay, little boys throw the rubber duck to the head of their fathers, but they cannot really fly. They were thrown, but they cannot fly. So there's a little problem in it if we have ducks different to the ducks we had before. Okay, what do? We can override the fly method, and that they cannot fly. So we have a solution for the problem. But always we have to think, it's a good one, or is it not? So, yes, the rubber duck can do nothing. We have a decoy duck. A decoy, it's an artificial duck, and it's mainly a female duck. You put it on the lake, and the male ducks think it's a real female duck, and they come to see this beautiful female decoy duck, and they were just killed. Okay, so beware of the decoy ducks. Okay, we have to implement the decoy duck, and it cannot quack, cannot fly, we have to change these methods. Is it really a good solution if we do this like this? No, it's not. I can tell you it's not. We try to solve it via interfaces. We have a flyable interface, a quackable interface, and we have a duck. So we exchange fly and quack special interfaces. Now we implement these special methods here. We have to implement a fly method here, a fly method there. And as you know, these fly methods are similar. Plenty of programmers make a cut and copy and paste. And we know that from yesterday, copy and paste is not a good solution. You have to try to avoid it. So you can see here, you would, in most cases, if you resolve it like this, you will do a copy and paste, and that we know it's not good. So we have a solution for the problem, but it's not a good one, because we have to make a copy and paste here. And at the end, it's not a good solution, because we have to, if we have different flyable ducts, maybe to the extent more flyable, more ways that ducts can fly. Or would we have to implement different flyable structure that is difficult to implement? We have now, you can see 1, 2, 3, 4, 5, 6, 7, 8, I hope I counted right, 9 connections between interfaces, abstract classes, and here are other real classes. How can I distinguish that this is an interface and this is an abstract class? Can you see it? The errors are different. This is an inheritance error, and this is an implementation error. Very easy to see. Everywhere in the world, computer scientists use UML, so this language, unified modeling language, is used everywhere. Quite fine. Why is this all German? Oh, I took the wrong file. Just a second. This is a German original, but I want to use the English one. Can we change the file? Okay. Switch, sorry. Okay. So we have a design principle, it's called encapsulation. Yes, it means I try to identify aspects in the application that can change and separate them from those that remain constant. It's quite an interesting principle because we have found out that we have a large application, thousands of lines of code. And if you have to maintain them, if you have to change, then we have found out that about 10% of the code, sometimes it's 5, sometimes it's 20, but it's at the end it's a small part of the code where you have to make changes all the time. And most of the code will remain the same over the years. It's an interesting thing we have found out. Why? Well, it is like that because one reason is that if you have data structures, they don't change a lot. So everything related to data structures will remain over the years the same. And anything related to human-computer interface programming is changing. Some new views of the system, some new algorithms. So what is close to the front will change more than what is in the backside, just to remain consistent. Okay? So that is one thing. So if we know that we have to do this, we know that only small parts of the code are changed plenty of times. So what is here? We solve the changing behavior out of the class with flying and walking. How does it look? We have the stack class we had, and we put out all what is different. Different is the flying behaviors and the walking behaviors. Because we know real ducks, okay, they can fly, real ducks can walk. But if we have other ducks, like rubber ducks or decoy ducks, then they cannot fly and they cannot walk. In real life, the examples are different, but this is a simple one, and I think it's a nice one. Also, there are not so many nice examples. So, we program an interface, not an implementation. So we define interface, and it's called fly behavior, and we have there the operation fly. And we know that this operation has to be implemented. Here we have two classes, one is fly with wings and one is flying away. So here we implement the fly operation for the ducks who can fly. And here we implement something where they do nothing. For the real ducks we will use this, and for the rubber ducks and for the decoy duck we implement flying away. If you like, little children who would implement not flying, but duck can be thrown. The rubber duck, and the rubber duck can be thrown from the head of the father. Ask Caesar, he has got two boys, and they have thrown rubber ducks at him plenty of times. So, and that. Okay, now let's look what happened. What's happening? Usually, I'm a software engineer. I try to avoid present code because you need a lot of time to read code. Programming to an implementation would be this is programming to an interface, and so at the end you have the implementation object at runtime. Let's look. If you have a dog, say it's a new dog, and the dog can bark. So you design program to an implementation to complete dog. An interface. You have an animal, and the animal is a new dog. And now you have, and this animal makes sound. You can the sound implement different. If you have another animal, maybe a cat, the cat is making different sound. But better is, give me an animal, and this animal will make some sound. So you make the distance even more if you do not program to complete implementation. But of course, I'm a software engineer, so you will always see these diagrams. Okay, we have now fly behavior, flying, real flying, no flying, and here you have a quark behavior, and you have real quarks of real ducks, you have the squeaks of the rubber ducks, and we have the new quark. Well, they cannot quark. The decoy dog cannot quark. Okay, fine. We have these interfaces, we have the implementations of the interfaces, that's fine. Okay, now how can we add rocket flying? We have a duck which can fly like a rocket. And how can we, do you know it's not a duck but can quark? Okay. How can we add rocket flying? I go back to, how can we add rocket flying?
We could add a new flight behavior for.
Exactly. Here comes the third class and rocket flying and implementing the flying behavior. So you have with one extension, you have a new fly behavior you can use from that moment. And do you know a duck that is not a duck but can quark? Well, that's a strange question. Because we have a special the hunters have special what does the referee in the football have in his mouth? A pipe.
Whistle.
A whistle. And you have special whistles that have a noise of a male duck, of a female duck, sorry, of a female duck. All the males are coming to see this beautiful female. Yes, the decoy duck swimming, but it cannot make noise, and you have a whistle, and you use this whistle and to create the noise that the male ducks will come run around and look for the beautiful female. But unfortunately, there is no beautiful female. There's only a hunter who is killing the ducks with Kawakami. Okay. So now we have two things. We have the fly behaviors, we have the quarking behaviors. Now we have to look at the abstract class duck. There we have an abstract class duck. We have two attributes. One is the fly behavior, and the second is the quark behavior. And as a operations, we have an operation perform quark and perform fly, and swim and display is the same. So, how is quark behavior working? We have a public class duck, the quark behavior, and we have a public operation perform quark, and then we have the quark behavior and it does quark. Very simple. Nothing hidden or no trick or something like that. It's just straight programming. And we have another class, the malloc duck. It stands duck. We have an inheritance. The malloc duck is all getting from the duck, but he has to implement the quark and the fly behavior. It can quark, and it can fly with wings. And then we have the display method. The display method has to be implemented because in this simple case, it just says I'm a real malloc duck. If it's a decoy duck, it says I'm a decoy duck, and if it's a rubber duck, it says I am a real rubber. So at the end, structure like this. We have an abstract class duck. From this abstract class, we can inherit all different ducks we want. And second thing, we have the fly behavior and the quark behavior. So, and now we have to just to connect the correct fly behavior and quark behavior to the complete ducks. If you want to add a new fly behavior, you add it here. If you want to add a new quark behavior, you add it here. And from that moment, you can use it on the other side. So the structure is always the same, and it's called the strategy pattern. And if you look Okay, we still have some connections between these classes. But the big advantage is that you have a very clear structure if you want to extend the structure. Yes? Okay, we'll go back. Have this in mind. 3 blocks. Everything is very clear designed. Now we go back. This one. And now think about adding something here. It would be a real disaster. You would have much more of these associations and inheritance things. And at the end, you do not know what to do. That's the main difference. It does work, but at the end, you do not know what you have done. Here, it's absolutely different. If you are a large group and you have to implement plenty of things, maybe you have one colleague who is responsible for the fly behavior, one colleague who is responsible for fork behavior, and others are implementing the real application. So you can split the work between the workers quite fine. So that is a big advantage. Okay, the design principle is prepare composition to inheritance. We have the composition of these behaviors to the classes. Strategy pattern, as it is known, defines a family of algorithms and calculates them individually and makes them interchangeable. The strategy pattern allows the algorithm to vary independently of the clients that use it. It's fine, you can change. Even we can change fly behavior in one of the classes. It's quite fine. You change this here. Flying with wings is now different. You're on another planet. Flying, they fly different. You just change exactly here. And from that moment, you can use it everywhere. So it's quite fine. We have a very good coupling and cohesion. We have coupled what is necessary to couple, and we have divided into separate parts, which has to be divided. Okay. Any questions to the strategy pattern? Any question? No? It's an easy one. And second is the decorating. It's a little bit more difficult. We have a coffee house chain with the name Starbucks. It has nothing to do with Starbucks. It's completely different. It's just an example. It sells coffee in different compositions and with different ingredients, and the first design looks like this. We have a drink or beverage. If you look and see, it's an abstract class. And you have different drinks, the house blend coffee, the dark roast coffee, the decaf coffee for people who cannot sleep in the night, and we have the espresso coffee. And each of these different coffees return to you what they do cost, because it's different. Now we want to allow ingredients for the individual coffees. These are calculated individually. If you want to have milk for it, you have to pay for it. If you want to have sugar, you have to pay for it. And anything else. So we have plenty of different coffees. For example, the espresso with whip and soy. We have here decaf with soy. We have here dark roasted with steamed milk and caramel. And every of these different coffees will give you its price back. If we look at this, even we don't know why they did it like this, it doesn't look fine. If you add a new coffee, you always have to create a new class, and you have to implement anything from the beginning. So you think about how can we change that? Is it possible to change it? And it is possible. It's called the decorator method. First, let's look at how the beverage class looks like. It has a description. It has the ingredients milk, soy, mocha, and whip. And it has operations to get the description and the cost operation. And it has the operations has milk, has soy, has mocha, set mocha, has whip, and set whip. And maybe other useful methods. Okay. Now we will implement it in beverage instead of food. We can have a look what's going on. Now we have an idea that the superclass is designing all these, and as a concrete cost operation, and we hope that it can make it possible to calculate the cost for each of these strings. But at the end, it doesn't work. I'll tell you why. Because there are plenty of changes we have to accept in the future, and we want to be able to we can react to these changes quite well. First, we have price changes for ingredients, so we have to make the change to the code. Milk is cost 10 rice more, 1 rice more, if you want to have more. Or things are changing. We have new ingredients that lead to new operations in the superclass. We have new drinks that may never need these ingredients. Or there are people who want twice as much milk or twice as much chocolate as the others. I have a colleague who likes a lot of sugar in it. So people like their drinks quite different. But you have to program that. Okay, let's look what is the solution. And we have to design the open-close design principle. Have you ever heard of it? It's quite famous. Classes should remain open for expansion or extension, but closed for change. So we try to keep classes, once they are correct, implemented. We don't have to change them anymore, but we like to extend them. Okay, let's look with how we can solve this problem with a decorator pattern. First, we have the cost of dark roast coffee, as an example. First, we know how it costs. Maybe it's 5 rice. So we can ask what a dark roast coffee does it cost. Now we want that mock-up to it. So we create a mocha object and wrap it around the dark roast object. So the mocha object is what we call a decorator. It type mirrors in the object, it is decorating, in this case, a beverage. By mirror, we mean it is of the same type. Interesting point, mocha is of the same type as the coffee. Mocha has a cost method too. For polymorphism, we can treat any beverage wrapped in mocha as a beverage too, because mocha is a subtype of beverage. It's a little bit strange. We usually have no feeling that a mocha is a beverage, but we implement it like this. Okay, the customer like me, I like to have a little drop of milk in it. So I want to whip. So we have a dark roast coffee with mocha and a whip. We decorate the whip around the mocha. It's still a beverage, and we can do anything with it. We can do with dark roast, and we call it cost method. That's the big point. So now we calculate the price. That's an interesting thing. First, we call cost on the outmost decorator, which is width. We ask, what do you cost? And he knows I'm a decorator, so he asks the next one, what do you cost? This one is also a decorator, so he's asking even the next one. But this is not a decorator anymore. This is the original coffee. So he gives back his 99 something, maybe dollars, 99 cents. This method. This method is adding 20. This is adding another 10. So these are added together and you get a price of 129. That's okay, fine. Now it's interesting how it looks in the diagram. You remember this strange diagram where we had these hundreds of different coffees with all these ingredients. This. We have components. The component has a concrete component. These concrete components are the coffees we have, the basic coffees. The decaf, the espresso, the house blend, I forgot one, dark roast coffee. Those are 4 concrete components. And we have different decorators. And now we have this even abstract. Now we have concrete decorators and we can add these concrete decorators. We have milk, we have soya, we have whip. I've forgotten something. Okay? So, if you see this structure, it's quite fine. And let's now look how it, yes, it comes. How it looks if we look at the concrete example. You have beverage, as I told you, the concrete components are the house blend, dark roast, the espresso, and the decaf. Everyone has a price. You can get it from the cost method. Then we have the condiment decorator, which is abstract as well. And here you have the condiments, milk, mocha, soya, and whip. So, they have a cost operation that gives the price tag of the milk. So what is necessary if the milk changes price? If just to modify this cost method. And from that moment you can use it everywhere. The house blend is increasing, prices are always going up, I don't know why. But if the house blend is changing, its price is going up, you have to change it here. So I always have a clear point where to change. It's quite fine. Maybe they make a week, and they say for 1 week a whip is free. You can make it. Just change the method and the head cost is nothing. You don't have to look at plenty of places where maybe there is any price for the whip. No, you have just one place and you can change the price here. After a week, you change it back to the price before, or even higher. Okay. So, that's the decorator pattern. And it's one of the, from my point, I like the observer most, but the decorator is quite fine as well. It's one of the smartest patterns, I think. If you do not have any questions, I will move now to another. Okay? I have to. last time. We ended last time on this slide factory. For people who haven't been here. The question is, where do we create objects? And I started last time to explain what we call a simple factory. So we have one place where we create pizza. This example. This is what we call a simple pizza factory. So it is designed that you have a operation, a class, you have this create pizza operation. It has an association to an abstract class of pizza. And for this abstract class pizza, the operation is prepare, bake, cut, and box. You have the concrete pizzas, which is cheese, veggie, lamb, and pepperoni. If you want to add a new pizza, it's easy, you add it just here. That's the point. You have one place where you create pizza. It's like in the pizzeria, one place where they are making pizza. Okay. You have been successful with your program. Now there are plenty of pizzerias in the country. You all want to use your program, but a little bit different because they have different pizza. Let's look. In the States, you have two famous types of pizza, if you go there. One is the New York pizza, and the other one is the Chicago pizza. Have you ever been to the States? Have you eaten a New York or Chicago pizza? No. Okay, I was with my oldest son, I was in 2000, I was in New York, but we only stayed in New York and we ate New York pizza. Thin pizza, not a lot of things on it, it's small, not a lot of cheese. It's for the New Yorkers who sit in the bureau and don't move to do a lot. If you go to the States, you have the New Yorkers. The other side of the continent, the Californians, who are not so fat. Plenty of other states, they have fat people because they eat more than they can afford. So New York pizza gives your New Yorkers a chance to stay thin. I think 2 or 3 years ago I was with another son in Chicago. And I knew this example, so I said to my son, once we have to go to a pizza shop and eat the pizza. And we had an American with us, and so we went to a pizza, and I said, okay, let's buy a pizza, and there came a pizza, and it was exactly of such height, a lot of cheese on it, and we couldn't eat it. Three men couldn't eat a pizza. And the American one took a quarter of it home. So it's very heavy, because Chicago is known as a working man's town. Yeah? In Detroit, they have the manufacturing of cars. In Chicago, they brought all the cows to Chicago and had a hard-working man to kill the cows, to put them into separate pieces of meat, and then the meat was distributed all over the country. So if you work in a factory like that, you need a lot of food, and you want good food that you stay strong. So Chicago is known for its food that is heavy. So you stay strong. Unfortunately, you get a little bit of fat. Okay, now, but for us, it's okay. We have New York pizza, we have Chicago pizza, and they want to make their pizza different. Chicago dish right here with thick crust, rich sauce, and tons of cheese. And I know it's true. The New York style pizzas have thin crust, tasty sauce, a little tasty sauce, and just a little cheese. So you can stay thin. Okay, first design is we make every pizza with its own factory. The New York Pizza Factory has a new pizza factory, and the Chicago Pizza Factory has a new Chicago pizza. And you can order, for example, here veggie pizzas in every of these pizzerias. Fine, let's look what you'd like to change. How does our unfortunately it's not translated. All paths have to move to we have to translate it right now. They have different procedures. They bake a little bit different. Maybe they don't cut the pizza, and they use packages, different distributions. Now, at the time we are looking at these new requirements, the code to produce pizza, prepare, bake, cut, and box is related to the pizzeria. But it's also flexible if we want it. So how we do it now? We change a little bit. This is now a very interesting thing. It's known because of this here. It's an the factory method. Okay, I will start with the top. We have an abstract class. The pizza store is now an abstract class. And it has the order pizza method. And in this order pizza, we have a create pizza. And this is an abstract description of an operation. We move the factory object into this method. So we give them a string which contains the type of pizza we want to create, and then we have to implement this create pizza method, this abstract method somewhere. Let's look now. Oh, you know the difference what abstract means? Abstract class, abstract method. You know what it is compared to a concrete class? Okay, now we have the pizza store, which is abstract, and we have the create pizza method there. It's abstract, and we have the order pizza, which is concrete. Now we have to implement these concrete create pizza methods inside these inherited objects. So, how does it look? Okay, now I have to show you code. We have this New York style pizza store, and we look at the create pizza method there. So, pizza method here, and if you want cheese, you create a New York style cheese pizza. If you want pepperoni, you want to get a new style pepperoni pizza. And if you want clam, you get a New York style clam pizza. And if you want veggie, you get a New York style veggie pizza. Same as here in the Chicago style pizza store, we have a create pizza method. And here it is exactly the same as it is here. In the one difference, we create Chicago style cheese pizza and Chicago style pepperoni pizza, Chicago style clam pizza. So at the end, we have two implementations of the create pizza method for operation, and one for New York and one for Chicago, and both are working. So where do we decide? We will decide in the pizza store. No, we don't decide in the pizza store. Create pizza is implemented into where in each subclass. So in each subclass, we decided how to create the pizza. Now look what's going on in the pizza store, we have the create pizza abstract method and the complete order pizza. And how does it look? The order method we remember is prepare, bake, cut, and box. First to create pizza, then we have to prepare, bake, cut, and box. How do we create pizza? Every pizza is doing it like itself, because we have to create. Create pizza method is concretely implemented into both of these classes, and you decide if you want to have a New York style pizza, that we use this class and this operation. If you want a Chicago style, you want a Chicago style, you use this class and this pizza operation. Okay. So we have here the New York style, New York pizza store, and that extends pizza store. We have the create pizza method, and the string contains cheese or veggie or clam or pepperoni, and then you can, these items, depending on what it's containing, you return the complete cheese pizza, veggie pizza, clam pizza, or pepperoni. But independently of what we have in the string, we create New York style pizza because we have a New York pizza store. Okay. Okay. You have to do something.
It sounds sharing.
Okay, no problem. Short. This was the last slide I just showed you. Now the question is easy. How do the code for Chicago pizza looks like? Let's look. Well, we have, well, it looks similar to this, with one exception. Where you see in New York, you always have Chicago. That's all. So let's look at the whole structure. We have this abstract class pizza store with the order pizza method, the create pizza type, and the create pizza. Abstract method, and so we call it the factory method, and we move it into this factory method. That is giving this design pattern its name. It's a factory method design pattern. So look at the factory method itself. A factory method is always abstract. It returns a product, which is an object, and you give a string with it, which is defining what kind of object will be created. Okay, now let's order pizza. Two of you, one is called Ethan, the other one is called Joel. Ethan wants to stay thin, so he wants to get a New York pizza. And Joel has just left his woman, so he don't get a lot to eat at home. So she wants Chicago style, so he's ordering Chicago style pizza. So they have the same ordering method, doesn't differ, but they want to have different kinds of pizza. Okay, how do we do that? First, Joel and Ethan need an instance of a pizza store. Joel needs to instantiate a Chicago pizza store, and Ethan needs the New York pizza store. With the pizza store in hand, both Ethan and Joel call the order pizza method and pass in the type of the pizza they want. Cheese, veggie, clam, or whatever. The different stores are offering. Then, the create pizza method is called, which is defined in the two subclasses, New York pizza store and Chicago pizza store, we have already seen. And the New York pizza store instantiates a New York pizza style pizza, and the Chicago pizza store instantiates a Chicago style pizza. In either case, the pizza is returned to the order pizza method. The order pizza method has no idea what kind of pizza was created, but it knows it is a pizza and it prepares, bakes, cuts, and boxes. I have to say a little different. Maybe a New York style pizza, because it's thin, needs to bake shorter than the Chicago pizza with a stick. So maybe this will take more time. But in this case, we have a simple solution. So, okay, let's look at Ethan's order. He says, I want a New York pizza store. On this store, I want a pizza. Now, if we have the store, we can order a pizza. I want to order a pizza and I want a cheese one. Okay? The next is that we created the pizza with the create pizza method, and it's a cheese pizza. We know that this is returning a New York cheese pizza. We know that. Finally, we have the unprepared pizza in hand, and the order pizza method finishes preparing. Prepare, bake, cut, and box. And at the end, it's at the box and deliver it. Okay, we're just missing pizza. Okay. Now, our pizza store, we have to implement different toppings, different sauces. So we have our abstract class. We like to use abstract classes to instantiate. So we have something for the name of the pizza, the graph, and the sauce. And we have an array list of toppings on the pizza. So now we have the prepare method. We now don't really bake, but we just do print line. We are preparing something, we're tossing dough on it, we're adding sauce, adding toppings, and at the end we do show what we have done. So we bake for 25 minutes. No, it's not Celsius, it's Fahrenheit. No difference of Fahrenheit and Celsius. Different measure of temperature. We have a cut, diagonal slices, box, and pizza store box. And then we return the name and it's ready. We have the New York pizza with standing this pizza method, and the New York style cheese pizza. The name of it is New York style sauce and cheese pizza. The thin crust, and it's a marinara sauce you put on it. And the toppings is grated Reggiano cheese. Special Italian cheese. As far as I remember, not as fat. And it does not, it stays even at higher temperatures as it is. Chicago. Now we have Chicago style dish cheese pizza. It's extra thick crust stuff and it's plum tomato sauce. And here we have shredded mozzarella cheese and quite a lot of it. And then we have to cut it. It's like two square slices. We have a different way to cut it. And yeah, then we have. Now let's test it. Let's test it. We have now 2 pizza stores. If you want a third one, we can add a third one. We have the New York store with the order pizza method. And with the Chicago store with the order pizza method. So now we can order from every store different, here now only cheese pizzas. If we let the project run, we have this print lining, preparing New York style sauce and cheese pizza, and it's costing putting Gruyere cheese on it, 25 minutes at 350, cutting the pieces into diagonal slices, place pizza in officer pizza store box, and we tell at the end, Ethan ordered a New York style sauce and cheese pizza. Then we have the Chicago style pizza for Joel. We put duff on it, sauce, toppings, shredded mozzarella cheese, same baking process. Here we cut it into square slices of a pizza store box, and at the end we tell Joel ordered a Chicago style cheese pizza. So we have the pizza store with the 2 methods, creator pizza and order pizza, where the creators are abstract. We have the New York pizza store, the Chicago pizza store, they have to implement this great pizza methods. Now we have the concrete pizzas every store is producing. It's cheese, it's pepperoni, it's clam, and it's veggie for both stores. So at the end we have the structure. We have the product classes, we have the creator classes, and yes, if you want to add a third pizza store, you can add it here. And if you want to add a concrete pizza, you have to add it here and here. So you have a clear structure of your creation process. You can create different pizzas. You have a structure where you can change quite easily. So a chaos is an order process. Most interesting sentences. Bottom of the line, factory method is the key in encapsulating this knowledge. New York Pizza Store encapsulates all the knowledge about how to make New York style pizza. The Chicago Pizza Store encapsulates all the knowledge about how to make Chicago style pizzas. So what is called the factory method pattern defines the interface for creating an object, but lets the subclasses decide which class to instantiate. Factory method lets the class declare instantiations to subclasses. So the general diagram for this is this one. You have a product, and an abstract product, and a concrete product. You have an abstract creator and a concrete creator. And if you look here, this is the most interesting side. The factory method is abstract, other operations not. And you have to implement the factory method in the concrete creator classes. Okay, any questions to this? So it's easier. Okay, so I would finish now. I think we can stop that because I now want to see that we get these files transferred.